Hello, everyone. First of all, I hope everyone is doing as good as possible given the current scenario. My name is Bruno Gabrich. I'm a PhD candidate at the University of Pennsylvania, and my co-authors are Guanrui and my advisor, Dr. Mark Yim. Today, I'll be presenting ModQuad-DoF, a novel yaw actuation for modular quadrotors. In our previous work, we have shown how modules could fly as independent units and self-assemble in midair into a variety of different structures, as seen at the animation on the right. Our inspiration for that comes from the South American fire ants, Solenopsis invicta, that with their own bodies can build bridges in midair connecting distinct regions in space. In previous work, and at this current work, we used the Crazyfly 2.0. It weighs 27 grams with a payload of 15 grams. Although, we don't use a single quadrotor, but multiples of them. Also because they are very small, they have a very limited force provided by the motors. In gray, we see the force we wish we could obtain from propellers, and in red, we see that the actual force provided is much less than we wish we could obtain. Along those lines, the figure on the top left shows a flying structure composed of 4 modules. The yaw actuation applied to each individual quadrotor relies on the drag moments from each individual propeller. As a structure grows, physical properties in actuation also grows. The inertia and moments in Z have a linear part with respect to the number of modules. Although, inertia also has another nonlinear component that is dependent on the position of each module. This makes inertia to grow faster than the yaw actuation, and behaviors seen at the animation on the right could be noticed as more and more modules are docked together. Since yaw is coupled with thrust, we also expect this up and down behavior. So, how to scale modular flying structures? In this work, our approach allows a one-DoF between structure and quadrotor. In previous work, both of them were rigidly attached. In order to implement this idea and scale the number of modules that cooperate in flight, we propose a new cage design, which is made of carbon fiber rods, 3D printed connectors, and square neodymium magnets. The attraction force provided by the magnets are enough to avoid unexpected in-flight undocking. The pendulum design was made with the objective to obtain a single steady-state position with respect to the quadrotor. Therefore, second-order disturbances are expected during flight, but our attitude controller is capable to reject these disturbances. Once we have 2 modules docked together, a new capability arises which could be seen at the figure in the center. With this capability, structure moments could be obtained by the independent row angles of each individual. Here we have some related work. The first one is a DFA from ETH, then we have Hollow from University of Tokyo, and last we have the Flying Gripper from Penn. In all of this work, the yaw actuation was either a problem or could be a problem. The approach used for all of them was also either tilting propellers or using stronger motors and bigger propellers. The method of having fixed tilted propellers could be an issue for scaling, once only half of the propellers will contribute to yaw in one direction or the other, and going for strong motors could increase the cost of the platform. Then here we present the dynamics of the system, in which we divided in translational dynamics and rotational dynamics. The translational part basically shows how individual forces affects the linear acceleration of the system, which is dependent on the orientation of the quadrotor relative to the structure. Second, we show a linearized rotational dynamics specifying how individuals' moments affects the structure moments. And third, we show how structure moments are affected by individuals' forces given the orientation of each quadrotor relative to the structure. Given the new method of yaw actuation, we made a scaling analysis by comparing how drag moments actuation increases relative to the actuation we are proposing. The comparison was made for a maximum of 10 modules in a line configuration. As we see in the plot, the novel yaw actuation provides bigger moments for a range of row angles compared to the drag moments yaw actuation. Here, we apply the solution of equal row angles for each module. Therefore, we can go to the control approach, which at some level is similar to the approach proposed in previous work. It relies on a centralized trajectory controller with force, thrust, and attitude distribution for each robot. In this work, the independent force distribution for yaw control was added given that each robot can have its distinct desired row angle. It's important to notice that with our approach, the robots doesn't receive anymore a desired yaw, once the structure moments in Z are now being controlled by each independent desired row. Going to the centralized trajectory controller and giving a specific position and yaw, we can compute the desired structure force and desired structure moment in Z. Once we have both entities computed, we transform it into n desired force vectors that are correlated to each specific module. This is made possible by applying the pseudo-inverse matrix, the pseudo-inverse of matrix S. This pseudo-inverse transformation minimizes the sum of all y components of these desired force vectors. Once we have all force factors computed for each individual module, the idea here is to transform that into input commands to each robot. The basis for that transformation relies on the well-known geometric controller approach. So in order to obtain thrust, we project the desired force factor in the world frame into the Z component of the frame of the robot. The process for obtaining the desired row and desired pitch takes the orientation of each force factor into account. One main difference from this work is that our B yaw is now a function of the current yaw instead of the desired yaw. Now that we have thrust, desired row, and desired pitch, we send these distinct inputs to each one of the robots. The last step of the controller takes place locally inside each one of them, so at the firmware level. A PD controller is applied in order to obtain angular accelerations. The integral term is omitted once that could bring instability to the system as a whole. Given the angular accelerations, the forces for each motor are computed given the position of each module relative to the structure and also how many modules compose the structure. Therefore, if this approach, modules can cooperate behaving as a flying conglomerate with improved yaw actuation that allows bigger structures to be formed. So going to the experiment section now, we see on the left two robots flying in a line configuration without the new yaw actuation. We see that oscillation happens even with small disturbances. Because of the coupling Z position, we also expect the up and down behavior. Now on the right, with our new yaw actuation, we see that the quadrotors tilt in order to control the structure yaw. And we see that the response of the system is much better, and the oscillations that we notice in situations where the new yaw actuation was off, doesn't happen anymore. Later, we tested 4 robots in a line configuration with drag moments for yaw control. Here we are sending a unique desired position space and different desired yaws. We notice that with 4 modules in a line, there's a lack of actuation that prevents the structure to go to the desired state. Now, on the right, with our new actuation on, we see that a much better response is obtained, and the tracking of the desired yaw commands are achieved. We notice also small oscillations, but that doesn't compromise the system. As a last experiment, we tested 6 robots in a line configuration. To the best of our knowledge, this is the first time that 6 crazy flies together in this kind of configuration. Similarly to previous experiments, a single position and different desired yaws are sent to the robot. We can see that even with such large structure, we are capable to keep it controllable. The bigger overshoots happens due to the tuning of the structure desired moments estimation. In fact, this overshoots is an indication of the yaw actuation improvement. Therefore, we can conclude that the new yaw actuation was validated for hovering conditions. The new controller approach was validated through experiments. Improvements for yaw controllability and reduced loss in thrust for 2, 4, and 6 modules in the line configuration were observed. In future work, we aim to explore configurations in which specific modules do not contribute to the yaw of the conglomerate, and also structures not constrained to a line configuration will be explored using the basis of the controller proposed in this work. So with that, I would like to say thanks to everyone that contributed to this work at some level. Also, thank you for listening to this talk. Stay happy and stay safe.